Thank you so much for having me. So I want to talk about cost. And I think it's easy to talk about all the amazing advances. It's easy to talk about all the big ideas and everything exciting. But I want to get to brass tacks and nuts and bolts on how much it costs to actually do this. I think without that, it's hard to talk about what's attainable and what's not attainable, and what's attainable for whom. I care a lot about getting this technology out there and letting everybody kind of define what we do with it, not just letting one institution or, I guess 3 or 4 institutions at this point decide how we're going to use this technology. And the first step there is making it cheap enough that everybody can actually work with it. So I actually want to start with a couple quizzes. So, think about this. I like to get up to hard numbers, and I hope that during this presentation you'll get some hard numbers. So ResNet 50 on ImageNet. This is an old kind of, at this point, computer vision benchmark. It's still pretty standard in a lot of papers and publications. Think to yourself about what the cost is. I would usually survey you, but time is short, and I want to cover a lot of numbers during this presentation. It's about $10 to train this these days. If, as a NeurIPS area chair, I see all of the complaints and rebuttals, if you are complaining that you can't afford to do this, you can afford to do this. Don't ever complain. I'm never going to let you get away with that. What about stable diffusion? It's about a year old now. Diffusion model trained on, I want to say, about 2 billion images. Does a pretty impressive job generating stuff. Think to yourself again, how much does it cost to actually train this? And these are on, this is just total cost of compute. We're ignoring annotations, data sets, all that other good stuff. I'd love to ask Angela at some point how much it costs to collect all of that RLHF data, but I'm sure that I would never get a straight answer on the exact number. It's a little fuzzy. We can talk about that over much stronger drinks than we just had. But stable diffusion is about 50K. That's not too bad. That's honestly, it's a pretty impressive model, and it's totally within reach. Training a decoder-only language model to GPT-3 Perplexity. This is not training GPT-3. This is training, a more modern model that would get to similar performance. We can't really say anything beyond GPT-3 because the details haven't been released for any subsequent models. But GPT-3, it's about 300K. That's not bad. That's a lot, but it's not $10 million. It is within reach for a lot of companies. It's bad. I'm not going to do that in my spare time. Maybe someone here might have the money to do that in their spare time, but it's not bad. What about BERT? And there's a lot of detail in this. This is basically how to define what it means to train a good BERT. And I've seen a lot of people cry when their NeurIPS reviewers ask them to train a BERT model. It's about $50. You can afford this for your paper. So this is all warm-up to say that I want to think about cost. This is a great chart that came out about a year and a half ago in a paper called The 3 Eras of Machine Learning, and it basically looks at the number of flops required to train whatever was the state-of-the-art network over time. And this is on log axes, so the cost is increasing exponentially. It's probably been increasing faster lately. But the takeaway is that training the current state-of-the-art model is increasing by about 200% to 400% per year. Moore's law was about 200% every 18 months. So this is going faster than Moore's law ever did back when Moore's law was still a thing. And one question I typically get at this point is, who cares about training cost? Isn't inference the big cost suck? Don't you, train a model once and then, run it on billions and billions of queries, and so actually inference is more expensive? And the answer is, well, there aren't really any good numbers, but this is one of the best that I have. It's a Google blog post from now a little over a year ago. And the claim, you can trust David Patterson or you can not trust David Patterson, but across all 3 years of preceding this study, about 2/3 of ML energy usage is for inference, and 1/3 is for training. Training hardware is typically more expensive than inference hardware. You have stricter memory bandwidth requirements. You need to have good interconnects between the chips. And so cost is probably closer to 50-50 here. And I'll let our friends at Google go and tell us whether this is true or not, wherever they are in the audience. I won't point any fingers. But this is at least one of the few public numbers that's quoted by a big company. Training is a huge portion of the cost. I imagine for our friends who are working on things like Gemini right now, it's an even bigger portion of the cost. And here we are. So there is this thing that I was told, and it's I was told this, I read this in a history textbook. There was once this thing called Moore's Law. And there was a nice phrase that went along with Moore's Law, which was Andy Grove, then the CEO of Intel, giveth, and Bill Gates taketh away. That is to say, our compute is getting 2x faster every 18 months, and our software was getting 2x as demanding every 18 months. But the nice thing was that over decades, the cost of using a computer and getting kind of state-of-the-art performance was remaining constant decades and decades and decades later as the performance increased exponentially and the capabilities increased exponentially. I would love that for deep learning. I would love it if every year we get 400% more ambitious, and every year things get 400% cheaper. So I want to do the math and think about how can we keep those costs in check, concretely. And now suppose someone showered you with a bunch of VC money and said, go do this. And lots of people are now getting showered with lots of VC money and getting told to go do things like this. So, me and, half the people in the world, it seems like. Now, the first thing you might do is build a chip. Traditional CPUs are not optimized for the kinds of operations we do in deep learning, and deep learning is actually a very small number of operations. So you would build a chip. This is a brilliant idea I just had, and unfortunately a bunch of other people got there first. There are a lot of chips out there. But now we can do some math. Let's assume that Moore's law is still somewhat in effect and call it 40% per year and maybe 10% per year on better neural network architectures or better chip architectures. I think that's overly generous, and I'll do some math. NVIDIA's told me not to. I got yelled at by NVIDIA for putting these numbers in here, but what the hell? Let's take the A100 released in November of 2020. I did literally get yelled at NVIDIA for calling them out on this, but they made plenty of money. They're fine. 312 FP16 teraflops. H100 came out, I got my H100s in June 2023, so I think May 2023 is fair. About 1,000 FP16 teraflops. Really impressive improvement. But now let's do some math. The price was $15,000 for an A100 plus or minus, system inclusive, so all the other components as well, 20.8 gigaflops per dollar. Now, I'm not going to talk about what the actual price of an H100 is, because this is where I get yelled at by NVIDIA. But I can say that an H100 would have to have, it would have to have 58.5 gigaflops per dollar to have kept up with this, which means an H100 has to cost the same as an A100. If anybody's looked at pricing recently on the clouds, yeah, no. It's a lot. It's like 2 or 3 times as expensive, probably even more than that. So no, hardware is not keeping up. OK, next, let's write a great compiler. The operations that we train a neural network on or that we use for neural network training are kind of not necessarily optimized for hardware. What makes sense to us doesn't make sense for the chip. Let's write a compiler. Again, a bunch of other people got there first. There are a bunch more I can probably add to this slide now. I'm generously going to give that 30% per year, and I'm going to quote PyTorch 2.0 here, which has torch.compile. They were able to get speedups up to 43% here. Keep in mind, PyTorch 2.0 was not a one-year project, and I'm looking at 30% per year, so this is a very generous overestimate for what we can get out of compilers. OK, now there's something really funny about all this to me. And it's that they're taking the math underlying neural networks and faithfully reproducing it to the bit, using a compiler to change the nature of the operations, but not the actual math that we're doing. Hardware that if you go from a V100 to an A100 to an H100, up to some little hardware level non-determinism should execute everything bit for bit exactly the same. And there's something very strange about that, because there is nothing sacred about the math behind deep learning. This is not like merge sort, where if you do it approximately, you're not going to get a sorted list. There's no such thing as correctness in deep learning. I mean, our data's all wrong anyway. We're doing all this fun convex optimization stuff in a highly non-convex loss landscape where we have literally no understanding for what's going on, and I will challenge any theoretician with a fancy proof in the room to go and tell me that they understand what's actually happening in these big neural networks. I will take that bet every time. You have no clue. And your infinitely wide 2-layer neural networks are very cute, but have nothing to do with reality. And you've got all this stuff. And if anybody wants to give me a definitive explanation for any of this, let me know. I once wrote a paper on batch norm and did a great survey of 30 different papers, each of which had a different definitive explanation for why batch norm works. It's the state of the science. We don't have good understanding. That's not a bad thing. It's just a fact. And deep learning is just approximate computing. There's no right answer. And in approximate computing, you can frame a problem, to get a network that reaches a particular level of quality meaning whatever you care about in terms of performance, as cheaply as possible. It doesn't matter how. There's no right way to do it. And the claim I'll make today is that algorithmic advances are going to be what get us that 400% per year if we're going to get there. We can change the math. There's nothing right about the way that we do things. The only reason we train ResNet 50 the way that we do today is because Kai Ming did that back in 2015. And nobody wants to shake up the formula because then the reviewers yell at you for changing your baselines. Same thing with GPT-3 today. I think there are aspects of the Llama architecture even that I look at and say, I think things could be a lot more efficient if we are willing to take some risks and change out X for Y. And this works. These are results that we got at Mosaic. ResNet 50, this is the traditional kind of hyperparameters that people tend to use in papers. We got it about 7x faster. And it was about 1 year by 5 researchers. This was not a monumental project. This is the recipe. It's all open source. You don't need to take a picture of this or write this down. We tried a bunch of different methods. Everything you see here is something we tried. The things in bold are the recipe. I'll talk in a moment, depending on how much time I leave myself, about coming up with a good recipe. It's tricky. Not just because something works in isolation does not mean it will work with a bunch of other things. There are interactions. There's some science to this. But it's not hard science. It's not that hard. And I love what our CEO said here. He's a hardware guy, so I'll quote this. Would rather invest $200 million into a new computing architecture and maybe get 2x, or spend less than $5 million, a lot less than $5 million, probably closer to $1 million, and get 7x with better algorithms. That's kind of the proposition here. There's a lot of headroom to push down the cost. And you can do this with BERT. You can get about 3x on BERT. You can do this with, traditional image segmentation. You can get about 5x there. And you can drive down the cost of stable diffusion. That 160K was kind of our best guess as to what it cost stability. It's 50K here. Internally, it's probably down to 30K or 25K now. GPT-3 quality for less than 500K, it's a lot less than that now. And these are prices we quote to customers. You can come and pay us to do this. So I want to talk science. How do you actually go about doing this kind of algorithmic improvement? And there are a few rules. Your goal is to reduce the time or money necessary to train a neural network. Time and money is very strict. I do not care about flops. Take your flops and go home. I do not care about sparsity. And for those who know my research, that's a big statement to make. I do not care about sparsity. I care about raw time and money. Anything else is made up and nonsensical. And if you're putting that in your paper, who cares? Quite frankly. And I do have to be a little pushy here, because now that I'm an area chair and I'm seeing the academic community get further and further left behind by what's happening in industry, some of it is resources, and some of it is self-imposed by the made-up frameworks we're still stuck in. And you have to break out of that. So there are 3 rules. The cost of inference cannot increase, first of all. You can't present your customers with a trade-off. You have to keep inference cost the same or lower when you do this. You can't just say, well, I trained a network 5 times as big and it learned a lot faster, but good luck on inference. It has to be the same. The hardware platform and software stack are fixed. You're not allowed to say, well, I moved to an H100, I made the algorithm faster. No. You're not allowed to say, well, I moved to CUDA 12.1. No, you have to actually do this by changing the math behind training. Rule number 3, you have to optimize your baselines. This is so dumb to say, and yet the number of papers that I've tested, papers that are very popular in the literature, that are getting a lot of hype right now, that are complete BS because they cooked the book on the baselines, or the baselines weren't strong enough. They optimized their own method and didn't optimize the baselines. It's a tale as old as time in the literature and in lots of other fields, but I feel like I have to say it because I've spent so much time reproducing methods and finding that they just don't pan out if you really look at them closely. I really should have rule 4, which is you have to optimize your baselines, just to be very clear on that. So I want to go through a method very quickly. I'm going to speed through this. This is one method. This is not a thing that I recommend you actually go and do, but I think it's a nice illustrative example of the art of how you actually do this work. It's called selective backprop. If I gave you a blank sheet of paper and said, write down what selective backprop is, you could write down this whole method right now. Got a neural network, you got some inputs, you get some loss values, and the backward pass is about 2/3 the cost of training. Again, a good rule of thumb. Drop the examples that have the lowest loss. The network already knows them. This is not provably correct. This is an approximation. You have to evaluate this and show that it seems to work in practice. But let's just take on faith that it works. And then you only backprop the 50% of examples at the highest loss. This will reduce the cost of training by 1/3, which is magical. We get our speedups in 5% and 10%. So 1/3 reduction in the cost of training would be huge. Now, this doesn't work. The big reason is because Torch AutoGrad does not let you go and do this operation. And if you want to do this operation, you can go and rewrite Torch AutoGrad and maintain a fork of Torch AutoGrad, and I wish you the very best. Don't do that. So instead, you can do another approximation. You can kind of do 2 forward passes, one to get the losses, then drop the examples, then do a second forward pass and a second backward pass. This cuts your gains in half, but you still get a 1/6 improvement, which is pretty good. Now, this kind of diminishes for various reasons, but that would be pretty good. Now, you can do more approximation to get back what you gave up. That first forward pass doesn't have to be exact. It can be approximate. You can do it on low-resolution images. You just need to get the overall rank ordering of the losses correct. So, the losses don't have to be right. They just have to kind of approximately be correct. And then you can go through and drop the examples. So, this is one example of the kind of stuff that we do. It's okay to break the rules. There's nothing sacred about the math behind deep learning. Okay, but now you have to evaluate success. And this is tricky. The simple answer here would be you get a network that's just as good in less time or money. If you're NVIDIA, That's what you do. V100 to A100 to H100, basically mathematically the same. As long as you made things go faster, you're good. Now, just as good is tricky for a lot of reasons. First of all, what does it mean to be just as good? You have to get your evaluation right, and that is probably the biggest open problem in the field right now. In the pruning literature, we kind of got burned by this. We were like, oh yeah, you can prune a network by 80 to 90% and preserve accuracy. Turns out you greatly bias the network when you do this. Oops. So you do have to be really careful about evaluation. But problem number two, what if you can't get anything just as good? What if I told you the following? I will reduce your accuracy on ResNet 50 on ImageNet by 1% for a 10x speed up. Raise your hand if you would take that. Raise your hand if you wouldn't take that. Raise your hand if I did not give you anywhere near enough information to evaluate this trade-off, because it's completely contextual. This is the problem with trade-offs. It's all contextual. So how do you make sense of this? Well, there's this cool thing I invented called the Pareto curve. It's named after, no, I did not invent this, but it feels that way because I never see this in machine learning papers. I just see these fancy tables with bold numbers that are incomparable. So again, clean up your act, everybody. But there's this cool thing. Yeah, you can call me Jonathan Pareto from now on if you want to. And this is my baseline. This is ResNet 50 on ImageNet trained for 90 epochs, reaching 76.5% accuracy in 3 hours and 33 minutes. Suppose I give you this point. This is my speed up method. Raise your hand if you would take this point, completely blind. You better have your hand up. This is both better and faster. How the hell would you not take this? What about this point? Raise your hand if you would take this point. Yeah, you should have your hand up. It's faster and the same quality. This is Pareto Curves 101. I have to give this to machine learning folks because it's as if nobody's ever heard of it. What about this point? Raise your hand if you would take this. Raise your hand if you wouldn't take this. Raise your hand if I'm doing this on unitless axes. And so you have no clue what this means. Yes, okay, good. What about this point? Would you take this? Raise your hand. Think so? Again, unitless axes. These could be like super duper logarithmic axes, and this could take the life of the universe and more compute than has ever been invented. Okay, anyway, so how do you know whether this point is worth it? The important part is then in asking the question, let's look at this point. Why did I train this for 90 epochs? Does anyone actually know why we trained ResNet 50 on ImageNet for 90 epochs? There's a really good explanation. Because Kaiming did that in 2015. And in fact, if you look at the literature, our accuracy on ImageNet has been creeping up over time because people have been training for longer to get SOTA. It's now not that non-standard to train for 600 epochs. Back in my day, it was only 90 because people want to get better accuracy. So that point on the right is no less valid than this point, trained for 45 epochs, or whatever this is on my unitless axes, or this point. These are all potentially valid baselines. And the important takeaway here is that your baseline is not a point, it's a trade-off between the cost of training a model and the accuracy, or the quality. And so when I look at this point, this is an improvement in the trade-off that I could attain before. This is better. I will take this point over my previous recipe, at least for this quality bar. And remember, that red point is also not just one point. It's also a trade-off. I can take that same recipe and train it for 120 epochs, or 600, or 50, or 1, and get this trade-off curve. And I consider a model to be better when it gives me a better trade-off between cost and accuracy. Pareto Curves 101. And whenever I quoted a speed up to you, I'm quoting this point. It's easy to look at this point and get it into one number, and people love numbers. So as I wrap up here, I want to show you a couple of real Pareto curves. This is a little messy, and I'm going to walk you through this. This is our results in ResNet 50 on ImageNet. The first thing to look at is that black line there. This is the other time I get in trouble with NVIDIA. This is just when you use the default NVIDIA hyperparameters. This is not calling out NVIDIA. This is calling out 2015 calls, and they want their hyperparameters back. And this is a very solid baseline sitting in the NVIDIA examples repo. That is something that lots of folks have beaten up on. Our friend Ross Whiteman, you can see the TIM examples here in blue. That is a recent recipe from early 2022, I believe. You can see our Pareto curves, and you can see there are three, mild, medium, and hot. These are named after, thank you Taco Bell for the inspiration. Eventually we'll have Diablo as our really long recipe. But you can see there are three Pareto curves. And there are a lot of considerations that go into picking the right recipes, one of which is the length of time you're training gives you a greater budget for regularization. And regularization is a slowdown in the short run and a speed up in the long run. And so mild is if you want to do well on MLPerf. MLPerf looks at 75.9% accuracy, which as you can see is kind of garbage these days, even if it's been standard for a long time. And medium for reasonable runs, and hot for longer runs. All these Pareto curves are better trade-offs than anything else out there for their particular cost regimes. But we came up with 3 different recipes that kind of stack up a little bit more in terms of methods. This is ADE 20K. Deep Lab v3, so this is image segmentation. You can see the red is us, huge improvements. And if you look at that blue line and you look really closely, anybody see the words there? Optimized baseline. This is actually a 2x improvement over baselines in the literature because you have to optimize your baseline. And it turns out our hyperparameters weren't that great. And then we built on top of that. So it's probably a 10x over what's done in the literature, but 5x over a fair, reasonable baseline. And then BERT, sorry for the matplotlib, who has time for actually graphing things nicely? There are lots of networks to train. But again, BERT, a solid 3x speed up. The nice thing about all this, as I wrap up, it's all open source. Go enjoy. We don't make our money off of having some secret recipe or some secret model. My business is to build really good infrastructure for training foundation models like the 30 to 100 billion parameter models in the world. And then people contract us out to train those big models for proprietary use cases. So we can share everything we do because we don't make our money off of secrets, we make our money off of good infrastructure. So it's all open source, the details are all there, the model checkpoints are open source, go have fun. And I will say from a scientific perspective, and this is really speaking to my NeurIPS reviewers, if you're out there, if you're looking at my BERT paper right now and thinking, wow, there's nothing novel here, they just combined a bunch of boring methods together that already existed, and what's interesting about that? I really think scientifically, this is empiricism on the bleeding edge in service of practice. I think that is the right way of looking at it, and I'm sad that it's so hard to publish that work. And I hope that we can create some space for people to get that out into the world. So with that, happy to take some questions.
Thank you for that incredible and humorously delivered talk.
Oh, nothing about this is funny. I'm very serious about this. I take my NeurIPS reviewers very seriously. I'm going to find you.
Okay. I think we have a question right here.
Thanks for the great talk, and then thanks for Mosaic. I've been able to actually, I was inspired by all your work, and then we're actually training all these large-scale language models privately at the Genentech and Roche. So
you should become our customer.
Oh, well, I don't know. Thanks to you, we can actually train it ourselves. So I don't know. We'll see.
Okay, we're never open sourcing anything again.
But that said, especially in the first part, you talk about how difficult it is to innovate, and then you had this speed up based on the, let's say, chip architectures or the, innovating on the compilers and whatnot. But also, algorithmic innovation is not that easy to come by every year. So how are you sure that that this is going to continue every year? Unlike the other things, it's possible that you already made all the improvements that you can, and then for the next, let's say, 20 years, there won't be any improvements, so that if you amortize it, then it's actually all the same thing, right? So how do you know?
It's entirely possible, but the way I look at it is there are lots of ways to improve, and this is just one strategy. This strategy is take a bunch of things and put them together to improve one training run. But I haven't even talked about data and making the best use of data and reducing the amount of data that you need for a model. That's a huge thing to be mined. We've still never gotten curricula to work in the deep learning literature as far as I can tell. Everybody has a curriculum result on CFAR10 that doesn't work anywhere else. And we've never gotten it to work. We all know that curricula should work or must work. There's plenty of work to do there. The other thing that really gets me excited is the idea that you never just train one model. Has anyone here ever trained one model and said, oh, I'm done? That was good. No, of course not. And the fact that we then throw away the first N models to produce the final model is a total waste to me. So we're doing a lot of research on recycling that compute and asking whether each incremental model can be cheaper and cheaper and cheaper to train. So I think there's so much room here. I mean, there's the headroom that I've showed here, 10x to 100x probably, and then there's all that additional headroom. I think we have many, many years before we run out of 400%.
Yeah, thanks for the great talk. In the beginning, you quickly dismissed compiler improvements or architectural hardware improvements as a way to go forward, but there is a sort of a breakpoint improvement where you could dismiss everything we've done so far, like throwaway phenomenon, and let's do something like neuromorphic computing. And I'm curious if you think our current hardware is eventually going to hit a wall, or if you think that is really going to get us all the way there with sort of what we have without a radical change.
I'm not a hardware expert, but I will say that my biggest beef with hardware people, any hardware people in the audience, by the way? Any hardware friends? You afraid to raise your hands? My biggest beef with all of you hardware people is you build awesome, interesting chips, and you never build software, and I can't use your chips. and I can point my fingers at every single hardware startup that's out there right now. So the answer is I don't know enough about hardware to actually answer your question, but I will say that it's all fine and good to have very innovative architectures. They have to be usable. And there's only one usable hardware architecture out there for deep learning right now. And I think that's kind of a shame at the moment. I mean, NVIDIA stock is doing exceedingly well. But my plea is, please show me that there's room to push the limits of hardware, and maybe show me that Moore's Law can kick back in. But for God's sake, build some software too. I want to be able to use it in PyTorch.
Maybe one last question. Oh, all right, Amir.
Great talk. Can you tell us a bit about the procedure that you go through for finding these algorithmic solutions that you have? How do you develop intuitions after doing it for one algorithm? Are they transferable across different models and algorithms? How do you go about it?
It's a complicated thing. I've thought a lot about this. One thing is there are good processes. There is just kind of keeping an eye on the literature and looking for opportunities, being willing to see the opportunities in papers that are not published and have been rejected, people who didn't have the resources to go big and trying to partner with them to help them go bigger. But honestly, I think our secret sauce, our real edge at Mosaic is cultural to some extent. We've just gotten a really, really good scientific culture when it comes to hardcore empiricism. I do think deep learning theory is kind of a waste of time, and I'm happy to say that. Any theoreticians in the audience, by the way? I'm making all the friends out here. But I think it's about really, really aggressive empiricism, being willing to just get your hands dirty and test things, even when things are really messy, test them at small scales and be willing to scale up. But it's really cultural, and the intuitions that we built over time. I didn't get, there's a bunch more to a longer version of this talk about kind of some of those ideas, thinking about Amdahl's law and which parts of a system you've optimized and which parts of a system you haven't, and looking for opportunities there. But it really is, to some extent, cultural, and that's our enduring advantage, I think, as Mosaic. It's not about the secrets. We can give those away, and it's still hard for people to keep up with what we do next.
Are they transferable?
So the question is, are they transferable? Can anybody name more than 2 architectures that anyone cares about today? Transferability doesn't matter. If it works for a decoder-only language model, and it works across multiple text data sets, and I've never really seen anything that hasn't worked across multiple different text data sets, there's only one architecture. In the diffusion world, there's really only one architecture. And so to some extent, it's been great for us because the world has converged. There are really only 2 networks that we train anymore. And so it doesn't have to transfer. You can really be hyper-focused on nailing 1 or 2 use cases, and that's awesome. It makes our lives a lot better.